over x minus a. All right, so this is going to be equal to the limit as x approaches a of f of x, that's my top left there, it's 4 over square root 1 minus x, minus f of a. So what would happen if I replace that x with a? I would get this all over x minus a. And this just doesn't look very fun because we have a complex fraction. So just like we have been doing before, what we need to do is we need to make a common denominator. So I'm going to multiply the top here by root 1 minus x, bottom root 1 minus x. Over here I'm going to multiply top and bottom by root 1 minus a, and then over here root 1 minus a. When we do that, we should get our common denominator. The numerator of the first top left fraction should now be 4 root 1 minus a. And then I will subtract from it the other one, which will be 4 root 1 minus x, all over the common denominator. That's these two are common now. So root 1 minus a times root 1 minus x. Then all of that divided by x minus a. What a mess this looks like. Okay, I don't see anything that cancels right away again. So in other words, I don't see anything that's going to cancel this out, so we don't have division by 0. So what I'm going to do is, because I see square roots, I'm coming in with conjugate. Top and bottom here, conjugate. Conjugate of what? Conjugate of this. So I'm going to go 4 root 1 minus a plus 4 root 1 minus x. And then 4, same thing, root 1 minus a plus 4 root 1 minus x. When I multiply the top together, okay, when I multiply these two, I do my FOIL up here. I get limit, let's see, x approaches a. I get the 4 times 4 is 16. The roots cancel, so I'm just left with 1 minus a, but that 16 will have to distribute to both terms. The middle terms will go away, and then I have the last two terms. So I get negative 16, and then again, the roots cancel. I'm left with 1 minus x, but that 16 has to distribute. All over this really, really nasty denominator, it's this times this. So I recommend that you just write that out. Don't try and multiply it out, just write it out, because eventually that's just going to be sitting there. It's not going to cancel. So 1 minus a times root 1 minus x times, in parentheses, 4 root 1 minus a plus 4 root 1 minus x, and all of that over x minus a. All right, look at that numerator for a second, this here. Let's just multiply some stuff out here. This is 16 minus 16a minus 16 plus x, or plus 16x. The 16's cancel, and what you're left with is 16x. So this turns into 16x minus 16a. Factor out a 16, you're left with 16 times x minus a. That means that when we look at the denominator as a fraction and bring it up and flip it up here, okay, so that'll be gone, then this top part, right, I know this is a mess, which is now 16 times x minus a, this and this will cancel. And so you're just left with that 16 on top and then that big ugly thing on the bottom. How great is that? Limit x approaches a. See, we had the 16 on top that didn't go away. And all this junk down here, square root 1 minus a times square root 1 minus x times 4 square root 1 minus a plus 4 square root 1 minus x. And now I'm ready to try and let x become a. If x becomes a, this will become an a, and this will become an a. So trying to do this without going to a new page. No more limit. We have 16 on top, nothing changed. We have root 1 minus a root 1 minus a again, 4 times root 1 minus a plus 4 root 1 minus a again, because x is a, right? This equals 16 over, all right, the first two terms here are the same thing. They multiply together, the root goes away, so I just get 1 minus a in parentheses. And then here, these two add together to get 8 of them. So 8 root 1 minus a. And that should do it. That is the derivative. That equals f prime a. Very, very nice. All right, that's it for examples. I think I've shown you a good mixture of, the different algebraic manipulations that have to be done in order to figure out these slopes and, as we can see here, the derivative. All right, let's talk about two very important concepts. Let's say you have an object, say a box here or something, and it's moving in a straight line. So we call this linear motion. Linear motion. Then what we can do if it's moving is we can talk about two things. First of all, its velocity, speed, and its acceleration. And if we graph this, in other words, we talk about, let's say we start measuring time, and then let's talk about the distance it travels. So at some point in time, this box is here, and then maybe another point in time it's here, and it's moving along. So at every point in time, right, this is t equals something. Another point in time here, t equals something else. And then different times, it's at different places. If I graph that, let's say at the first point in time, let's say it's here, and then later on it's here, and then later on it's, let's say, here. If we connect all those dots together for every point in time, maybe we get some sort of curve like this. And I don't know what it does. It does something like that. Okay. Then what we have is a distance versus time curve, and this right here is a function which we will represent by s of t. We will call it its position function. What it is it's a function that tells us where this box or car or bullet, whatever it is at every point in time. All right, so that's the s function here. Then if we look at the slope of the tangent line at some point, that slope of tangent line will give us our instantaneous velocity. It'll give us the velocity of that object at that point in time. So what we would need to find the slope of that tangent line is we would need to find the derivative of this at that point in time. Let's call that point in time A. So what we have is this, the velocity at t equals A. We're using t instead of x here because t is a better variable for time. The velocity at t equals A is the derivative of s at A. And this gives us what we call the velocity at A. Okay, so we'll call it v of A. This is very important. Now, since v of A, right, is velocity, turns out that if we take the derivative of the v function, we get acceleration, the acceleration of the object. The acceleration at t equals A is the derivative, the derivative of the velocity. And we'll call that A of A, even though A of A is kind of weird. But A here being acceleration, A here being the point. So this is a very, very important result in this class. If we have linear motion, something moving, and we know where it is at every point in time, right? If something moving, we know everywhere it is at every point in time. Then we can also tell anybody the speed it is at any point in time by just finding the slope of the tangent line or the derivative. And then we can also take derivative again and find the acceleration at any point in time. So let's take a look at an example. I'm looking at number 12 out of this section. It says, let's say that h is equal to 58t minus 0.83 t squared. Okay, let me just pop this book open real quick to make sure I state what this problem is saying. This is number 12. An arrow is shot upward with a velocity of 58 meters per second. Its height in meters after t seconds is given by this equation. So here t is seconds. T is measured in seconds. And h here, the height, is measured in meters. And we had an arrow, here's the ground, we had an arrow that was shot up, goes up and then starts coming back down. So this is linear motion, straight up, straight down. So let's just ask ourselves real quick. At t equals 0, what's happening? At t equals 0, you plug 0 in here, you get 0. So that means the arrow was on the ground. At t equals 1, where is this thing? Well, you get 58 times 1, which is 58, and then you subtract, let's see, 1 here, 0.83 times 1 is 0.83. So 1 second later, you're at 58 minus 0.83, so you're a little less than 58 meters high. So let's say if this is 58, we're a little bit less than it after 1 second. And then for every second, you know, we could try different points in time, and then we could figure out, you know, where it is. That's the basic idea. But let's talk about the questions here. First, find the velocity at 1 second. So how fast is this thing going after 1 second? B, what's the velocity at t equals a? So at any point in time, what's the velocity? C, when will it hit the ground? And then last thing, D, what is velocity when it hits ground? So this thing goes up, right? And we want to know first of all, how fast is it going 1 second after it shot up into the air? Then we want to know how fast is it going at any point in time. Then we want to know how long is it going to take to hit the ground, and then at what speed it hits the ground with. So overall, what we're going to need to know is the velocity of this thing, right? We need to know its velocity at 1 second and at t equals a seconds, and we also want to know what the velocity is when it hits the ground. So let's determine what the velocity is. Well, the velocity, okay, velocity at any point in time should be equal to the derivative of this thing. Well, right now it's called h. So I'm going to call it h of t. And I'm going to say the velocity is the derivative of that. So what I want is, I want the derivative of that h function, or the slope of the tangent line, at some arbitrary point t equals a. So at this point, what I can do is I can take my derivative. Now, I'm going to use either definition, but I think I'll go with this one. Limit, I'm going to go with the other one. H approaches 0. Now, the derivative of h at a is going to be h of a plus h minus h of a. So I'm just using h instead of f. And then all over h. All right, this is limit, h approaches 0. Okay, what we need to do is plug in a plus h into our function. So remember, our function is up here. Plug a plus h into this. So we should get 58 times a plus h minus 0.83 times a plus h squared, then minus, what is f of a? Well, f of a is 58a minus 0.83 a squared. then all of that divided by h. Now I'm going to save you some time. I'm going to just write down what all that is. You have to multiply this out, distribute. You'd have to expand that, then distribute, and then distribute the negative through here. If you do all that,